Hi folks, I miss you all. If this is the 2020 class. If you were just absent from class and using this video in the future, hi. So this is Physical Science Module 13. I'm just going to lecture through the whole chapter. And then I'm going to shoot a different video for the study guide, and then I'm going to shoot a different video for the 2 labs for Module 13. So you'll have hopefully 3, maybe 4 if I have to shorten a video, total videos to cover Module 13. So we start out with the parts of the atom. So we know that the basic building blocks of the atom, the main subatomic particles are, the biggest one is the neutron, which has a neutral charge, neutron, neutral. The next biggest one is the proton, which has a positive charge. And the smallest particle is the electron, which has a negative charge. So those are the 3 major subatomic particles. The proton is much bigger than the electron, but their charges are equal and opposite. So even though their masses are very different, their charges are exactly the same, just that the proton is positive and the electron is negative. Inside the nucleus of an atom, you have protons and neutrons, and then orbiting around the nucleus, you have the electrons. Every element that can be found on the periodic table, there's my periodic table. If you've had this class in person, you know I lose my periodic table like every 15 seconds. Hold on. Okay, so if you look at your periodic table, every single box on the chart is 1 element, each unique element. The way that we define what an element is a set of all atoms that have the same number of protons. And we use the number of protons because they are fixed in the nucleus. Their number doesn't really change unless we're talking about like a radioactive or nuclear event. So they're much easier. Protons are much easier to keep track of. Electrons orbit, and they're able to flow and be exchanged and participate in chemical reactions. And so it's much harder to account for the electrons. The proton number is very consistent. And so we define elements as a set of nuclei that have the same number of protons. So let's see. The periodic table is set up with metals on this side, nonmetals past this jagged line over on this side. And the periodic table will be very helpful to you all as you study the Bohr model in this module. The columns all share certain chemical properties, the way that they react, their reactivity, their what they want to bond with. So the elements in row 1 of the periodic table all want to give up 1 electron to have a chemical reaction. They want to bond with things in row 7 over here. They share a lot of really similar properties, very reactive. Row 7 also very reactive, nonmetals. The elements in row 8A over here, those are very non-reactive. They have a full outer shell of electrons, and so they're already in a very low energy state and don't want to react. So you can look at the periodic table's columns and see trends in the chemical properties. And so let's see. When we look at each individual box on the periodic table, we can learn quite a bit about the element it represents. For example, we have hydrogen over here. The number, or the H, stands for hydrogen. That's its chemical symbol. Every chemical symbol has a capital letter, and then some of them also have a lowercase letter. And so you can tell when you're writing a chemical formula for a compound, you can tell where one element begins and the next element begins, because each element starts with a capital letter for sure. And if there's a second letter, it will be lowercase. So H stands for hydrogen. The number 1 above the hydrogen in the box is the atomic number, and that tells us the number of protons. Every single hydrogen is defined as a nucleus that has 1 proton. And then below the hydrogen on your periodic table, it says 1.01, and that's the atomic mass. And there is no hydrogen that actually has an atomic mass of 1.01 atomic mass units. That is an average, which brings us to the topic of isotopes. So an isotope is a collection of nuclei that all have the same number of protons, right? They're the same element, but they can have a different number of neutrons in their nucleus. So there are 3 isotopes of hydrogen, for example, that are naturally occurring, and then there are some that are lab created, which we're not going to look at. But the 3 isotopes of hydrogen, hydrogen 1, and all it has in its nucleus is 1 proton and 0 neutrons. Hydrogen 2, which has, of course, 1 proton because it's hydrogen, and 1 neutron for a total of 2 things in the nucleus. And then hydrogen 3, which has 1 proton because it's hydrogen, and 2 neutrons for a total of 3 things in the nucleus. And if you look at how much of each isotope occurs in nature, you'll see that 99.98% of all hydrogen atoms are hydrogen 1. And then 0.02% are hydrogen 2. And there's a very rare trace amount of hydrogen 3 occurring. It's actually kind of hard to find, like, how much. So when you average the hydrogen 1s at the rate they occur naturally with the hydrogen 2s at the rate they occur naturally, that's how you get the atomic mass of 1.01 for hydrogen. So hydrogens all have a mass of either 1 or 2 or 3, but on average, hydrogens have a mass of 1.01 atomic mass units. So isotopes, even though the overwhelming majority of hydrogens are hydrogen 1, we don't say, oh, there's hydrogen 1 and it's 2 isotopes, right? We say, oh, there are 3 isotopes of hydrogen that occur in nature, right? All 3 of them are isotopes. And if we look at carbon as a good example as well, you can see here, if you look on the periodic table, in row 4A, if you're looking, I hope, at your periodic table, you see carbon. Its chemical symbol is a capital C. It has a number 6 above it, which stands for the fact that every single carbon nucleus has 6 protons. And then it has an average mass. I think your periodic table just says 12.0 for the atomic mass. But when you get periodic tables in college with more sig figs, you'll have 12.01 or maybe 12.011 for carbon. And that tells us that even though the vast majority of carbon atoms are carbon-12, meaning they have, of course, 6 protons and then 6 neutrons to add up to 12, 98.9% of all carbon is carbon-12. You also have carbon-13 and carbon-14 isotopes, which occur at a lower rate. And when we add up an average based on the proportion of how many of those occur, we get an average mass for carbon of 12.011, I think 2, going on like that. So that atomic mass on the periodic table is an average, but each individual carbon atom will either have 12 things in the nucleus, or 13 things, or 14 things. I think there are lab-created isotopes of carbon too, but these 3 are predominantly the ones that occur in, well, entirely the ones that occur in nature. Okay, so when we look at hydrogen and carbon, we actually find that both of these elements have one isotope that is radioactive. In hydrogen, we find hydrogen 3 to be radioactive. In carbon, we find carbon 14 to be radioactive. And a radioactive isotope is an atom with an unstable nucleus, one that will undergo decay. And I'll teach you the 3 kinds of decay in a minute. Both of the isotopes here, hydrogen-3 and carbon-14, undergo beta decay. So we'll look at those in a little bit. First, I guess we'll look at the Bohr model of the atom. So now we know that we have the protons and neutrons in the nucleus. Then we have electrons that orbit the nucleus. Now we've talked about gravity and how planets orbit the sun and how the moon orbits the earth. And so Niels Bohr made a model of the electron orbiting the nucleus similarly. We know this is not the case now, right? We know that electrons are far more complicated than a simple planetary style orbit. But this is a helpful model that allowed science to move forward. And so let's take a look at kind of how this works. So the Bohr model places the protons and neutrons in the nucleus. Please do not make dots on your test. Just write the number. Okay, so you can see here I've written in the nucleus, well, I hope you can see, number of p's standing for number of protons. So you could, for example, if you were talking about carbon, you would write 6p to stand for 6 protons in the nucleus. And then number of n's, so for carbon, 13. Since 6 of the 13 things are protons, then 7 are neutrons in the nucleus. So you would write 7n if we're talking about carbon-13, for example. And then you circle that for the nucleus. Okay, so that first circle is not an electron shell. It's just the boundary of the nucleus. Okay, then when we look at the Bohr model, the first Bohr orbital has 2 electrons possible in it. In the case of hydrogen, since hydrogen only has 1 electron, you would, of course, only put 1 electron in the first Bohr orbital. And then helium would have 2. If you go on to larger elements like lithium, which has 3 electrons, you would need to move to the second Bohr orbital because the first can only hold up to 2 electrons. Right? You can see I have made dots on the first Bohr orbital for the 2 electrons, and I have made dots on the second Bohr orbital, which can hold 8 electrons. Beyond the second Bohr orbital, I do not want to count dots when I'm grading. My eyes are too old for that. So you can see on the third Bohr orbital, I've written 18 electrons. And on the fourth, I've written 32 electrons. And on the fifth, I've written 50 electrons. And those are the maximum number of electrons that those orbitals can hold. But depending on the element, they may have fewer. They just may not have more. So just fill in the number of electrons. Just write the number. Do not write 32 dots on an orbital for me, please. I don't want to count those. Or, 10 dots. Just don't. So let's see. With the Bohr orbitals, if you look at the periodic table when you're taking the test, and you should have your OK for test periodic table when you take the test, if you are a bit confused about these numbers, say you think, oh, well, the first Bohr orbital has 2, the second has 8, how many is in the third again? The periodic table can actually help you if you haven't quite memorized those numbers of electrons in the Bohr orbitals. And here's how it helps. The first Bohr orbital has 2 electrons possible in it. And you can see the top row of the periodic table only has 2 elements, hydrogen and helium. Right, so 2 electrons stand for those first 2. The second Bohr orbital can have up to 8 electrons. And if you look at the second row of the periodic table, you see 8 elements, starting with lithium and going across to neon. 8 elements. So that's the second Bohr orbital. The third Bohr orbital, it gets a little complicated, right? Because you have the 8 in row 3, but if you look at the D block, if you look at these transition metals here, there are 10 of those. And even though this looks like it's in row 4, it is actually part of the third orbital. So the periodic table is a little confusing there, but in truth, the third Bohr orbital is the 8 in row 3 plus these 10 transition metals in this row. So that's 8 plus 10, 18. Then for the fourth, you can see what I've drawn in green, maybe, I hope. Can you see these highlighted in green? right? So there are 8 elements in row 4 from potassium, calcium, gallium, germanium, what do we have there? Arsenic, selenium, bromine, krypton, those guys. And those plus the second row of transition metals that are 10 here, 8 plus 10, that's 18, plus the first row, the lanthanide series down here. So the 8 plus 10 plus, I think this is 14 down here, gives you the 32 in the 4th Bohr orbital. Right, and then the 50 gets even more complicated. But I'm just telling you the periodic table can help you in remembering those numbers for the Bohr orbitals. So let's see. Going on to what would be day 2 if we had class. Let's talk about the forces in creation. So we've studied the 4 forces, maybe 3, depending on how you look at it, in creation, right? We've studied the gravitational force. We've studied the electroweak force, which could be split into electricity and magnetism, and the weak nuclear force. And we've looked at the strong nuclear force in general. But we want to focus our attention on the fact that, let's take, for example, a carbon atom, which has 6 protons in a nucleus. Now, what did you learn when we did the electroscope lab about how positive charges react to each other? Or when we talked about lightning, how do negative charges react to each other? And of course, you know that like charges repel each other. So how can we pack 6 positive charges, protons, into one nucleus at very close distances when all 6 of them want to repel each other very much, right? So that repulsive force, because they're the same charge, positive, should force them apart. That's the electroweak force. But the strong nuclear force, the strongest force in all of nature that we know of, tells us that if the protons and the neutrons, which also participate in the strong nuclear force, are close enough together in a nucleus, they are able to exchange tiny particles called pions. And this particle exchange allows them to have this tremendously strong force between them that overcomes the repulsive force from electromagnetism. And so it's an attractive force, as they have to stay close enough to exchange these very short-lived pions. They must stay at very close range to do that. So this very strong force keeps your nucleus together. The weak nuclear force governs things like light, electromagnetism, electricity, magnetism, and radioactivity. But the strong nuclear force is the reason that we don't see the 6 protons in a carbon nucleus repelling each other and coming apart, right? We have then a discussion of radioactivity. So there are 3 types of radioactive decay that different elements, with different isotopes of different elements, can undergo. The first one that we're going to talk about is beta decay. And beta decay is when an unstable nucleus has one of its neutrons actually become a proton and emit an electron. So we know that the neutron is the largest of the 3 subatomic particles, and a neutron is actually the size of a proton plus an electron plus a little tiny bit of mass. So what happens with beta decay is that neutron actually decays to a proton, emits an electron, and that tiny bit of mass becomes energy. So that, we'll talk way more about that in later years. That's super complicated. That was like the very condensed version of beta decay. So you still have the same number of things in the nucleus because there was a neutron and has become a proton and given off an electron. So if you had, say, in carbon-14, which undergoes beta decay, you had 14 things in the nucleus, right? In that case, 6 were protons because it's carbon, and 8 were neutrons. One of those neutrons becomes a proton, right? So now you have 7 protons in the nucleus. If we look at our periodic table, what has 7 protons? And it's nitrogen. So nitrogen has 7 protons, and so when carbon-14 undergoes radioactive decay, beta decay, it becomes nitrogen-14. Still the same number of things in the nucleus, but one neutron has become a proton. It will emit an electron, which then can start to orbit. Let's see. Beta decay, of course, emits an electron, and all radioactive decay can be, dangerous to humans and other stuff. If you want to be protected from beta decay, you can use like a sheet of thin metal. The radiation given off cannot pass through thin metal, for example. So that would be able to shield anything that you did not want to experience the radiation from something like carbon-14 or hydrogen-3. The second kind of radioactive decay we want to talk about is called alpha decay. And alpha decay is when an unstable nucleus emits just a helium nucleus, which is made up of 2 protons and 2 neutrons. Right, so a helium nucleus, helium has 2 protons, 2 neutrons, and that is what is emitted when something undergoes alpha decay. Even a sheet of paper, something flimsy like a sheet of paper, will protect because even though protons and neutrons are quite tiny, incredibly small, they can't pass through a sheet of paper. So alpha decay is not as concerning, basically. So you're emitting a helium nucleus. Both beta and alpha decay lose kinetic energy fairly quickly, and so just a solid distance between the source of these radiations and you would provide safety. We studied how electromagnetism is governed by an equation that has distance squared in the denominator, right? So you're exponentially safer the further distance you are from the source of radiation. Then the third kind of radioactive decay is gamma. And gamma is when an unstable nucleus emits energy with a very super short wavelength. And gamma radiation is very unsafe for life and everything. And it takes multiple inches of like lead to protect you. You would have to be like in a lead container, lead box that's very thick to be protected. So it's emitting energy, it's emitting photons with a very short wavelength, high frequency, dangerous. But gamma decay does not actually change the nucleus at all. It's simply emitting energy, but the number of protons and neutrons does not actually change. So cells that are hit with radiation can die, or their DNA can be mutated. Distance will protect you, depending on the type of radiation. Paper or foil or lead walls would protect you. And when we're talking about radioactive decay, each isotope that is radioactive has a unique half-life. And the half-life is the number of years or minutes or seconds that it takes for 1/2 of the nuclei in a collection to undergo radioactive decay. So half of them undergo decay during a half-life. And we'll talk about that in the lab. So I think that's all I wanted to talk about in the lecture. Next video will be for the study guide, and then we'll have a video for the lab. And I know some of you have done some of this in class already, but hopefully that was a good review. I miss you all, and I will send you an email shortly.